over the worksheet, projectile motion number 1. Key points here. Number 2, recognize that the package is moving with the plane. And so as it drops, its inertia wants to keep on going. It's not going to just drop straight down. It's going to keep on going with the plane. Number 3, you got this cliff, 80 meters high, it crashes over here. The truck does this. Okay, this is not a triangle. Do not draw a triangle there. Okay, don't try to do trig there. The biggest thing that will kill you if you did this, don't take numbers, information from the horizontal side and the vertical side and stick them into one equation. Okay, that would be death. Okay, do not take numbers from here and numbers from here and stick them into one kinematic equation. Make sure this is independent than this. They need to be separate things. Okay, the only thing that ties those together is time. Okay, so never take numbers from here and numbers from here and stick them into one equation. Even if you're desperate, that would be horrible. Quick demonstration. Okay, this cart launches something straight up when it passes this trigger. So the question is, what's going to happen if I roll this? It's caught. Okay, pause and try to figure out why. All right, so what do you say? Why did the ball get caught? Inertia definitely has something to do with it. I wonder. I think that's. Let's see what happens. All right. As I'm holding the ball, is the ball moving relative to you? Is the ball moving relative to you? Am I moving relative to you? Yes. Therefore, the ball is moving relative to you. Okay? Now, let's say I'm moving at 2 meters a second, and I throw it up at 5 meters a second. Okay? To me, this just looks like I'm throwing it up at 5 meters a second. Goes to a certain height. It's in the air for a certain amount of time. Okay? But if I'm walking at 2 meters a second, to me, this looks exactly the same. There's no difference. But to you, it looks like this. Right? Okay? So, as I'm walking at 2 meters a second and throwing it up at 5 meters a second, it still goes to the same height. It's still in the air for the same amount of time. The only difference is we're now adding a horizontal motion, horizontal component to that. But because the horizontal motion is independent of the vertical, how high it goes isn't changed, is not altered. It's still in the air for the same amount of time, all that stuff. So do you see why 4 and 5, why you can calculate stuff in number 5 without needing a calculator? You just look at number 4's answers. Does that make sense? Okay. So So, number 5, I'm moving at 2 meters a second. 2 meters a second, the ball continues to move at 2 meters a second the entire time, even up to the highest point. Okay. Vertically, though, it starts with an initial velocity of 5 meters a second. Starts to slow down at the highest point, vertical velocity 0, and it speeds back up in the vertical direction. Good with that? Okay. Now, if I found the resultant of those two, cut and paste, and I found that to be 5.39 meters a second at 68 degrees. That's how fast it was going overall. If the ball had a speedometer on it, as I was walking at 2 meters a second and threw it up at 5 meters a second, it'd be moving overall at 5.38 meters a second at 68 degrees. You all right with that? Okay. How are we doing so far? Tracking with that? Now, rarely do you have a scenario where you're moving horizontally and throw something straight up. Usually what they'll say is you threw a ball at 5.39 meters a second at 68 degrees. So you threw a ball like this. Instead of walking at 2 meters a second and throwing it straight up. This path is identical. The path the ball takes it, throwing it up at 5.39 meters a second at 68 degrees is identical to walking at 2 meters a second and throwing it straight up at 5 meters a second. Same path, exactly the same. Because when you go at 5.39 meters a second at 68 degrees, you're doing 2 meters a second horizontally, 5 meters a second vertically. You okay with that? And that leads us into number 6, which I'm going to explicitly teach today. Okay. So, break out your calculators. Let's say I throw a ball at 5 meters a second at 37 degrees. I want you to calculate the horizontal component. So let's say I throw a ball. My initial velocity is 5 meters a second at 37 degrees above the horizon. I want you to calculate the horizontal component. Thumbs up when you have an answer. Hopefully your answer is close to 4. If you got that right, tell your neighbor how you did it. Stretch. Okay. What trig function did you use? Cosine. Okay, so you find that side to be 4. Tell your neighbor what that communicates. What is 4? What units is it? Like, what does that mean? What is the significance of 4? Okay. What? Okay. Important point here. Whatever the units of this, that has to be, no other option, has to be the units of that. Has to be. If you ever find yourself with different units, you're wrong. Okay. So, what is this? 4 meters a second. What is that telling us? Beautiful. This is how fast it is going dying here. Horizontally. How fast we're going horizontally. Tell your neighbor what happens to that velocity, 4 meters a second, over time. If I throw this at 5 meters a second at 37 degrees, what happens to the 4 meters a second over time as time passes? Thank you. And tell them why.
So the vertical velocity changes with horizontal unless
Correct answer is stays the same. Why? No force is acting on it. Inertia is doing what it wants to do. Okay? Good with that? 4 meters a second the entire time in this scenario. That is going after 4 meters a second, 4 meters a second, 4 meters a second, 4 meters a second the entire time. Okay? All right. Find the vertical component. Yeah, find the vertical component. Tell your neighbor what it is and how you got it. Hope you got 3. I would recommend using sine over tangent. You can use it, just a little bit risky. Okay? Tell your neighbor what 3 communicates. What is the significance of 3? What's the units of 3? And what happens to 3 as time goes on?
Oh no. 3. Try it again. Design. No,
Good. As time goes on, at 3 meters a second, slows down, stops, and then speeds back up. Because it's experiencing acceleration. Good with that? Okay. When I say overall, I'm talking about horizontal and vertical, like the resultant. Thumbs up when you have a guess. Have a conversation.
Oh, true.
Correct answer is? Correct answer is B. This talks about the vertical velocity. This talks about the horizontal velocity. At the highest point, your vertical velocity is 0, but you're still moving horizontally. You okay with that? Okay. That was. Did you pass up the answer keys already? That was letter F on number 5. Good with that? If you could pass up those answer keys. Okay, next question. Thank you. Thank you. Thank you. Tell your neighbor. Okay, what do you say? B. Is this scenario different than the demonstration we did yesterday? Why is it different? This, you're throwing it up. If you're throwing it horizontally, then it hit at the same time. But this question would be like this. If I dropped this and threw this one straight up, which one from the same height at the same time, which one's going to hit the ground first? Wow. Mind blown. It's the same thing. You're just moving horizontally as well. Okay? They're not going to hit at the same time. The one that dropped is going to hit first because its initial vertical velocity is 0. This initial vertical velocity is positive. Okay? All right. So, ball is thrown at 30 meters a second at 20 degrees. How long is it in the air? You're going to do a couple things. First off, you're going to draw your initial velocity vector. Your initial velocity is 30 meters a second at 20 degrees above the horizon. Okay. Next thing you're going to do is you're going to draw your trajectory, the path taken. I want to know how long the ball is in the air, so here's my initial, here's my final. And then the third thing I want you to do is do your chart. There's a lot of setup involved, but it will help you consistently get the right answer. Okay. Now, 30 meters a second, which side should we put that in? Where should I put that in my chart? 30 meters a second. Hopefully you're thinking, that's weird. I don't know. I mean, it doesn't really do either. Perfect. That's exactly what you want to think. It's not. You don't stick that in there. It's not going purely horizontal and purely vertical. That is where our components come in. We need to separate this out and say, well, how much is this going purely in the horizontal direction, and how much of that is going purely in the vertical direction. Just in general, if you ever have a vector at an angle, whether it's a velocity, acceleration, a force, you're probably it's gonna be beneficial to break it up into components. How much is going purely in the x direction, how much is going purely in the y direction, because they are independent of each other. Rarely will that be a waste of time. How do we do? Thumbs up if you're tracking, thumbs down if you want me to come over.
So is this the initial cost?
Mm-hmm.
Why? I thought it was zero.
If you're launching horizontally, yes. But if you throw it at an angle, no. Does that make sense, the distinction? Okay, so what do we do with those? That is what goes in our chart. Okay, now, is that zero? When would it be zero? If you threw it horizontally. We're throwing it at an angle. So there's a vertical component, and that's 10.3 meters a second. Good with that? That's what you do with the 30 meters a second. Break it up into components, and now it goes in your chart. And now we're trying to figure out how long with the time in the air. Well, and then your fun facts of free fall come in. I know my acceleration. If it goes up at 10.3 meters a second, how fast is it going at the bottom here? Negative 10.3 meters a second. I can find time. So I have this kinematic equation. I'm going to modify that for the vertical direction. Yeah, in the glass cabinet. Or I mean, they're all glass. The big one. Yeah, top shelf to the left. Oh, is that one? Okay. Yep. Yep. Yeah. Get them. Yeah. Uh, Doc has the other one, but I have the hand cranks. Yeah, that one sometimes works. Can I turn one of these and turn the other one? Occasionally. I do the plastic ones. The blue plastic that does more. No, they're unreliable. They're what? Unreliable. Yes. Okay, so we get a time. 2.1. And then last thing, if it asks for the range, that's asking for delta X. Think of it like a golf range, not math class range, but like how far it goes horizontally. You're going to a golfing range. So, you take this time, stick it in here, and then that's delta X. Okay, got a worksheet due on Friday.